Okay, so your Section 5.1 notes are referred to as an introduction to polynomials. And the truth is, you have been working with polynomials. We just don't inherently call them polynomials as often as we are about to. For example, a line is a polynomial. A quadratic is a polynomial. And some of the actual new parent functions that we've been looking at, a cubic, for instance, also a polynomial. So our job today is to really understand what does it mean to be a polynomial and what can I determine from looking at polynomial functions, just their equation alone, their function alone. So I'm going to start with the first word here that's in your notes. It's the word monomial. Excuse me. And I'm going to give you a minute with each of these to write down the actual words that go along with them. And I'll just remind you what I mentioned to you yesterday, which is that I am going to check these notes for having filled them out. So you do want to take the time to do this for me, please. The first word is the word monomial. And a monomial is defined as a real number, a variable, or product of a real number and one or more variables with whole number exponents. I'll give you a second to write that down, but also write down examples that go along with it. For example, x is a monomial. 2x squared is a monomial. 4/5, x to the 5th is a monomial. Why? Because every single one of them has a real number, not an I, not an imaginary number, a real number coefficient, and is a product, can be a product attached to a variable, but the variables all have whole number exponents. The following are not monomials. Ix. Why? Because it has an imaginary coefficient. You could have 3x to the 4/5, not a monomial. Why? Because you have a non-whole number exponent. Also, just as a reminder, in case you forget, the exponent of -4, 2x to the -4. The 2 is legal, but the -4 is not because it's a negative exponent. These have to be whole number exponents, 0 and they're positive integers. Those are monomials. Each of those has a degree. The degree is defined as the exponent on the variable. So when I ask for a degree of a monomial, that is the exponent on the variable. So in this case, I'll put the degree up here, up above. The degree of 1x is 1. The degree of 2x squared is 2. But because of the exponent, not the coefficient, the degree of 4/5 x to the 5th is 5. The degree of 4x to the 7th is 7. Also a monomial is just the number 5, an integer. Technically, even though you don't see it, it has an x attached. What is its degree? 0. That's considered what we're going to call a constant. That is the degree of a monomial. When we start to put monomials together, we have a polynomial. A polynomial is a monomial or the sum of monomials. I'll give you a second to write that down. A polynomial is a monomial or sum of monomials. To be clear, we also have a few subsets of that idea. So for example, a binomial is when I have two monomials added together or subtracted together. We call it two terms. A trinomial, these are all words we've been using, is 3 terms. The key here is that these are where monomials are being added or subtracted together. So, on the next slide down below, a polynomial will also have a degree. The degree of a polynomial is defined as the greatest exponent of the polynomial. Another way to say that would be the greatest exponent of all the monomials. That's another way to say that. So, for example, when I have the polynomial 2x cubed plus 5x squared, the degree is the highest power on the variable, so in this case, 3. If I were to have, I'm going to squeeze in one right here, if I were to have another example, say 5x to the 7th minus 4x to the 10th, the degree is 10. It is the highest power on the variable, regardless of the coefficient. Now, you see another definition there. We're going to typically put polynomials in standard form. Standard form is where we arrange the terms of the polynomial by degree in descending numerical order. So notice the polynomial down below in your notes. 4x cubed plus 3x squared plus 5x minus 2. That is considered to be in standard form. That's considered to be in standard form. Now we're going to go ahead and talk about the details of this. The 4x cubed, the power or degree on that monomial individual piece is 3. 3x squared, that degree is 2. The linear term has a degree of 1. The constant term, you might want to add this, has a degree of 0. We've got the spinning wheel of death there. There we go. It's got a degree of 0. The degree of the entire polynomial, hopefully you're getting it at this point, the degree is 3. Why? Because it is the highest degree on the variable. As you turn the page, you're going to notice that you have two different polynomials. Go ahead and put those in standard form. Now what I'm going to ask that you do is take a minute and you look down on your paper and start to write. And when you're ready, I'm going to do the same here on the smartboard. You can check these. I'll give you another about 10 seconds. Notice that each of these is in standard form. I've got in part A, I've got 9x squared plus 3x plus 5, quadratic, linear, and constant. In part B, I listed x to the 4th first. I then put negative 6x squared and 10x squared together to give me 4x squared. I have to combine like terms. I then put the 4x as the linear next and the negative 12 as the constant, but the directions go further. What is the classification of each polynomial by degree? This is a review of algebra and even ideas that we've talked about so far this year. This is obviously, I hope obviously, this is obviously a quadratic. This is obviously, although you may not remember this term, this is considered a quartic. Then also it says classify by number of terms, and we just mentioned this. This has 3 terms. We've used this a lot already this year. This is a trinomial. And once you go above 3 terms, you have, in this case, just a polynomial. There's no special name for 4 terms. Go ahead, if you would, and this time, just double check. I'll give you enough time to write it down, answer the questions, and then check your answers. In letter A, you have your 4th degree coming first. Go ahead, though it doesn't ask for this, will you go ahead and please list the degree of each of these? The degree of this polynomial in A is 4. The degree here is 5. 3 terms on the left, the highest power is 4, it's a quartic, and that is a trinomial. The 3 terms on the right are also a trinomial. That 5th degree is a quintic. That's also a word you may or may not remember from algebra. On the next slide, we're going to go ahead and start to talk about some new ideas that we haven't necessarily addressed before in algebra. So these are going to be new to Algebra 2. And I'm going to talk about them, and then we're going to look at them. We've actually been dealing with some of these characteristics a lot. We just have used different wording or perhaps referenced it a little differently. The first word we're going to talk about is the idea of turning points. A turning point is a place where the graph changes directions. Specifically, and I'd like you to add this to your notes for me, it's where the graph changes from increasing to decreasing, from going up to going down, or it might be where it changes from decreasing to increasing. A turning point is like a maximum, a small maximum, or a small minimum. And the truth is that you have turning points in quadratics, for example. We just haven't called that a turning point. We've called that a vertex. That's where it changes, if we read the graph from left to right, it's where it changes from decreasing values to increasing values. When it's flipped upside down, that vertex is also a turning point. In this case, where it's flipped upside down, the graph is changing from increasing to decreasing. Those turning points, we've actually seen a lot of times, we just have different words for them. In a cubic, though we've just started to look at this a little bit more, you have this S-shaped picture, and here you have a turning point here and here where it changes from increasing to decreasing to increasing. Also with the polynomial, though we have not used words like this, it is, we talk about the phrase end behavior. The end behavior, I'll give you a chance to write that down, are the directions the graph is headed to the far right or the far left. And I want you to get those words down. Those words there, or that phrase about end behavior is not going to make a ton of sense yet, but we're going to talk about it more and more as we get going. The key phrase I want you to also write down is this. What is the graph doing at the extreme ends? Another way to say it is, what's happening as x approaches infinity? That arrow is a mathematical word for approaches, or as x approaches negative infinity. One other key word to write down, or key phrases to write down, are this idea that I just threw out there, but we're going to talk about all these characteristics here in a minute. One is the idea of increasing, and the other idea is that of decreasing. Increasing is the part of the graph that the y values increase. And I want you to write down this phrase, as x values increase. We always reference increasing and decreasing, write this down as well, as we read the graph from left to right. So when we talk about decreasing, it's the part of the graph that the y value is decreasing when, as x values increase. Now, that might not make a ton of sense yet, so hang tight and we'll talk through that. When I'm talking to an empty room, it's hard to know how much time to give you. So you might need to pause the video here to get down the rest of the definition. I'm going to go ahead and keep moving, but I realize you might not be totally done writing. So as we start to look at these characteristics, we do so in context to several polynomials. Starting with, first, this just basic quadratic. And we're going to start to point out several things. First of all, that is considered our turning point. Secondly, why is it our turning point? Because as we read the graph from left to right, this graph changes from y values that are increasing to y values that are decreasing. So we would say that this is increasing on the interval, starting at the beginning, and stopping at that vertex, which occurs at 1. And then it decreases from 1 to infinity. Now this starts to get some tricky notation, and we're going to talk through this quite a bit in the next couple of days. So don't panic if the notation worries you. Worry more about, can I trace? Can I trace when it's increasing? Can I trace when it's decreasing? And then can we talk about end behavior? And end behavior is what we're talking about when you approach infinity or when you approach negative infinity. Now you'll notice that this is x squared, some sort of quadratic. And in both these cases, my y values are going down. So what we say is, as x approaches infinity, y approaches negative infinity. Or, that's saying from here to here, my y values are going down. Or as x approaches negative infinity, y approaches negative infinity. Now that's not true over here. This is like a cubic of sorts. You'll notice that if we were to trace this, realistically, I don't see any turning points. It doesn't mean that other cubics don't have them, but there is no change here. The truth is that this is increasing the entire time. If I were to put my pencil, and I encourage you to do the same, on the graph, it's going up, 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 up. Even when it's slowly going up, it's still going up. As I read the graph from left to right, those y values are always increasing. In this case, we would say this isn't decreasing. My end behavior is a little different. In this case, as I look at the extreme end, as x values are going this way, notice my y values are going towards infinity. On the other hand, as x approaches negative infinity, my y values are approaching negative infinity. Now that's a little different, and one of the things I'm going to encourage you to think about is what's causing the difference. We've loosely addressed it in our parent points, but we'll continue to address it more later. In this case, we also have a cubic of sorts. Will be my parent point. There are two turning points here. In this case, I'm going to estimate them. This is at about negative 1 point, I'm going to make that up, negative 1.8, negative 1-ish. And this is at 1, 1. So I would say there are two turning points. Why? Because at this first turning point, it was decreasing, then increasing. So that first turning point at negative 1.8 is where it changes from decreasing to increasing. So I actually could say that it decreases from negative infinity down to negative 1.8. Then it changes to increasing at 1.8, negative 1.8, sorry. And it continues to increase until when? That second turning point. Well, when is that? At an x value of 1. You'll notice we're using the x values. That's because it's my x values that are telling the when, the story of when. When does it change? And then, what does it do? It decreases again. So it decreases from 1 to infinity. Now we're going to talk about end behavior on this. So we say as x approaches infinity, meaning as I go out this way, what are my y values doing? They're going towards negative infinity. And as x approaches negative infinity, y approaches, notice, they're going up to infinity. Now again, have on your radar, because we're not going to address all of this today, have on your radar, notice the difference. This is similar to the previous cubic. It does have turning points when the others did not, but more importantly, this end behavior is close to, not exactly the same, but similar to the cubic. Different than the quadratic. Have that on your radar. We'll talk more about that on Monday. In the meantime, I'm going to tell you that this parent function here is x to the 4th. And what I'd like you to do then, please, is see if you can list how many turning points there are. Can you name them? Where are they? And can you tell when it's increasing decreasing, and what the end behavior is. Go ahead and do that. I'm going to fill this out here as well. And then you can just check this. You'll notice I've gone ahead and listed the 3 turning points this time, which means you're going to have several different decreasing and increasing intervals. Notice that I use the x values of the turning points to list the increasing and decreasing intervals. Pay close attention to my answers with where the negatives are, especially because that one I estimated is 0.3 and negative 0.3. Notice that this end behavior, both of these are approaching infinity. How am I reading that? I'm reading that as the graph goes left to right, what's happening? Or, I'm sorry, as the graph goes at the extreme ends, what's happening? So as x is approaching negative infinity, what are my y values doing? They're going towards infinity. As x goes towards infinity, what are my y values doing? They're going towards infinity. Again, what I want you to slowly make connections to is, what is that similar to? The cubic or the quadratic? So when you look at this, we want you to start to think about what is the end behavior of the graph. Now here's what I'm going to ask you to do. I want you to put in 4x cubed minus 3x. And I'm going to ask you to go ahead, and your job on this portion is to pause the video and then put it in your calculator and decide what is the end behavior. And can you start to see patterns? What is causing the end behavior? Our goal by Monday is to draw some pretty grandiose conclusions about all of this. For now, we just want you to put it in your calculator and see what you can conclude. Put it on pause. When you're ready, unpause, and we're going to write down the solutions. Go. Your end behavior, in this case, since it's a cubic, it's going to have some sort of shape that looks like this. Now you may have turning points, but the key is that as x approaches infinity, the y's will do the same. And as x approaches negative infinity, the y's will do the same. On your radar, you should start to comprehend that a little bit. Because if I cube a number that is positive, it stays positive. If I cube a number that's negative, it stays negative. So the further out you go in either direction, it should follow that pattern consistently. Your end behavior in number 3 is that as x approaches infinity, y approaches negative infinity. As x approaches negative infinity, y approaches negative infinity as well. This is a quartic. When I take any number and raise it to the 4th power, it will become positive, but that negative 2 is causing it to go down. When I take a negative number, raise it to the 4th power, it becomes positive. Multiply by negative 2, it will go down. So the key there is starting to recognize the impact the power has on the end behavior and the impact that coefficient has on the highest power, also known as leading coefficient, as well. Now the directions say here for 5 and 7 add information about turning points, increasing and decreasing. And that's where we're going to start on Monday. So your job for the weekend, I'm actually going to pull it up here. Your job is to, hang on, awkward pause. There's a delay on my lovely computer. Maybe it's under here. There we go. Here is your homework. You'll notice what the homework asks. Part 1 says, write each polynomial in standard form, classify it by degree and number of terms. Done. Part 2, describe the shape of each cubic by determining the end behavior and number of turning points. What I want you to do for 16, 17, and 18 is please put that in your calculator. On your homework, you should state what the end behavior is, just like we just did. And using your calculator, determine the number of turning points. Please list those. On this section, determine the sign of the leading coefficient and the degree of the polynomial. This might get a little trickier. So what I want you to notice in 19 and 20 is, can you start to think backwards? Notice there are only 2 of those. Can you tell me about what power this is? About what power this is? Do you have an idea of what that could be? It also says, give the areas of increase and decrease. That you should be able to do. The first part might feel like you're guessing a little bit. I want you to use our notes, see if you can make an educated assumption. Increasing and decreasing you should be able to do following the methods, the examples I just gave. Down below, classify those. I don't need you to do all of these. I need you to do the odds. I'll list this on Schoology as well. On the odds 1 through 15, I need you to do 16, 17, and 18. I need you to do 19 and 20. And I need you to do 22 and 25. There's your assignment. Have a very nice weekend. Happy Friday. Bye, folks.